Hi, my name is Cedric Gentil, and I will present you our work on Gaussian process gradient maps for loop closure detection in unstructured planetary environments. Before introducing the core of our method, I will rapidly express the motivations behind our work. State estimation is the core component of every autonomous system. In unknown environments, the pose of the system and the map of the environment are simultaneously estimated. A key feature of such frameworks is the ability to detect loop closures when the system observes a previously explored area. It allows for the correction of the inherent drift present in the pose estimates and enables the generation of consistent maps. While place recognition in urban environments is a well-studied problem, unstructured environments still represent a major challenge for traditional vision and point cloud-based methods. As illustrated by the images from our Mount Etna dataset on the right, this type of environment does not contain distinctive visual features. Additionally, the exploration nature of planetary missions lead to heterogeneous camera viewpoints. In this work, we perform loop closure detection by combining a novel representation of the 3D terrain geometry and the robustness of 2D visual descriptors and matching. Our framework uses gravity-aligned point clouds of newly explored areas as input and is divided in two major components. The first one is the transformation of the 3D point clouds into Gaussian process gradient maps. It is a continuous and probabilistic representation of the variation of the terrain elevation. The second part is the matching and registration of 2D features extracted from the new Gaussian gradient maps and from the Gaussian gradient maps of previously explored areas. In the scenarios we consider, there is no overhanging structure in the vicinity of our system. Consequently, we can model the elevation of the terrain z as a function of the x and y coordinates. Using Gaussian processes to model this function and the application of linear operators to the GP kernels, the partial derivatives of the elevation with respect to x and y are analytically inferred from the point cloud data. The partial derivatives are combined into a gradient value as the norm of the partial derivative. In this slide and the following one, we provide a rapid overview of Gaussian process regression and the application of linear operators to obtain the partial derivatives. We recommend the viewer to read the cited work if seeking more details. Let us consider the elevation signal f. Using a zero-mean GP to represent that signal corresponds to characterizing the covariance between instances of that signal with a kernel function k. Given noisy observations of f, the elevation and its variance can be inferred probabilistically for any input value as the result of conditioning a multivariate Gaussian distribution. While the standard GP regression provides advantages compared to the use of raw geometric data, working directly with the elevation is not invariant with respect to the altitude of the map anchors. In other words, two point clouds of the same area can have different origins due to the pose estimation drift of the system, and consequently result in different elevation values. To address this issue, we choose to work with the gradient of the elevation. Given the Gaussian process model of the geometric data, the partial derivatives of the elevation can be analytically inferred with the application of linear operators. This results in the equation displayed here, where the differentiation operator is applied to some instantiation of the covariance kernel function. These continuous models allow for the generation of image-like maps as shown here on the right. Given two image-like GP gradient maps, we can leverage techniques from the traditional image processing literature. We extract 2D features in every map available, but features extracted in high variance areas of the map are disregarded. While our framework can be used with any 2D feature type, our implementation uses sub-features and descriptors. The sets of features in pairs of GP maps are matched together according to a brute force strategy and a L2 proximity metric. Given a set of associations between two gradient maps, we perform a SE2 Ransack-based registration. First, a pair of feature associations is randomly selected. From this, a SE2 transformation is estimated by aligning the centroid and performing a SVT decomposition. Knowing this transformation, a set of inliers is constituted using a distance threshold on the transformed features. Then, the transformation is refined according to the new set of inliers. To accept or not this transformation as a loop closure candidate, we use thresholds on the number of inliers found and the sum of squared differences between the registered gradient maps weighted by the inverse of the variance. The above process is repeated until a good transformation is found, or until a maximum number of iterations are already being performed. In this section, we will discuss experiments and results proving the soundness of our framework. Our experiments have been conducted using real-world data collected with sensor suits that comprise a stereo camera, an IMU, wheel odometry when integrated in a rover, and a differential GPS for ground truth reference. The geometric data needed as the input of our pipeline is generated by a submap-based SLAM system. The creation of a new submap is triggered by a threshold on the distance traveled, or if the estimated pose uncertainty is too large. Each of the submaps is converted into GP gradient maps. The previously explored area is therefore represented with a collection of GP gradient submaps. The colors in the video correspond to the estimated traversability of the area by the rover. 5 datasets have been collected with these sensor suits. 4 of them come from the rover exploration missions on Mount Etna, and 1 is recorded in Morocco with the handheld sensor package. The graphs on the left represent the system trajectories as seen by the differential GPS with the color gradient corresponding to the timestamps. The videos on the right show footage of the expedition to Mount Etna during which multiple types of missions, including robot collaboration, have been experimented. Both experiment sites in Mount Etna and Morocco have been chosen for their similarity to real space exploration scenarios. As explained in the motivation section of that video, planetary exploration scenarios are challenging for place recognition. State-of-the-art loop closure detection is especially suited for autonomous navigation in urban environments, but appears to be failing on our dataset as the environment lacks very distinctive features, and different viewpoints of the same area can greatly differ. This graph represents the precision versus recall results obtained with one recent method found in the literature. The light blue curve corresponds to the results obtained on an urban sequence of the publicly available KIDI dataset. While providing some results on dataset Etna 1 and 2, it performs poorly on Etna 4 and fails by doing worse than random on Etna 3 and Morocco. In this slide, we present results obtained with our novel pipeline against results obtained with methods based on geometric features directly extracted from the point cloud data. Each of the precision recall graphs is obtained by varying a parameter of the corresponding method. In the case of our GP gradient map method in purple with the label GPSurf, we varied the number of inliers required to declare a loop closure candidate in the RunZack registration process. These graphs show the performance gain of the proposed method with respect to existing methods across all the datasets. Our method also allows for loop closure detection in Etna 3 and Morocco, where the appearance-based method from the previous slide completely fails. The plot on the right illustrates a pair of submaps classified as loop closure in the dataset Etna 3. In conclusion, we presented a loop closure detection method for unstructured environment based on the Gaussian gradient maps. This novel representation is a continuous and probabilistic approach to model the variation of elevation in the environment. The loop closure is detected with a RunZack-based SE2 registration. As the method only requires point clouds as input, the proposed pipeline is agnostic to the sensing modality. Therefore, loop closure and relocalization across systems with different modalities is possible. The validation of cross-modality place recognition represents part of our future work, alongside with a real-time implementation of our method leveraging parallelization on GPUs and the use of bag-of-word schemes to reduce the number of RunZack registrations. I hope you enjoyed this video. If you have any question, do not hesitate to approach us. Thank you for your attention.